Hello, chemistry students. This lecture is about chemical equilibrium, and in this video, you will learn about types of reactions, rate of a reaction, dynamic equilibrium, equilibrium constant, direction of equilibrium, Le Chatelier's principle, and equilibria for heterogeneous reactions. Let's start with types of reactions. So far, we have assumptions that reactions go to completion. However, this doesn't happen all the time, and sometimes reactions never complete. And based on this, we can divide reactions in two types: irreversible reactions and reversible reactions. Reactions that proceed to completion in only one direction, that is the forward direction, are called irreversible reactions. In these reactions, reactants are completely converted into the product in a certain interval of time, and the products do not form reactants again. Example for irreversible reaction is burning. Burning is an irreversible change. When you burn wood, you get ash and smoke, you get carbon dioxide and water. You cannot change the ash and smoke back to wood again. And if you cannot convert the product back to the reactant again, then the reaction will actually goes to completion and will be only going in one direction, which is the forward direction. The second type of the reaction is the reversible reaction. These reactions actually proceed in both directions, forward and reverse. These reactions never go to completion and they always continue in both directions. In these reactions, product will form the reactant again. So in the forward direction, reactants will form the product, and in the reverse direction, the products will form the reactant again. Here I have the example of ice and water. At 0 degrees Celsius, ice and water are in a reversible reaction. There will be a balance between freezing and melting point. The liquid H2O will convert into solid H2O, and solid H2O will keep converting back to. This hydrogen iodide is an unstable product. It will actually decompose back to its reactants. When it decomposes back to its reactants means it is going in the reverse direction. So this reaction actually proceed in both direction. The reactants are making product and product is making reactant. So this reaction will never complete. Another example that I have here is nitrogen gas plus oxygen gas giving 2 moles of nitrogen monoxide. This nitrogen monoxide is unstable and will decompose back into a reactant. So this reaction is proceeding in both directions, forward and reverse, and will never go to completion. The product will be making the reactant again, and same is with this third reaction that we have. The rate of a reaction or reaction rate of a chemical reaction is the measure of the change in concentration of reactants or change in the concentration of the product per unit time. A rate law or rate equation is used to describe the relationship between rate of a chemical reaction and the concentration of its reactants. So let's write down the rate equation for this reaction that I have here. So this reaction is a reversible reaction. It proceeds in forward and reverse direction. So there will be two rate equations for this. One will be the rate of the forward reaction, and then we will have the rate of the reverse reaction. So let's write down first the equation for the rate of the forward reaction. So rate of the forward reaction, we write it as R is for the rate, F is for the forward. Rate of the forward reaction is directly proportional to the concentration of the reactants. We write reactants in the square bracket. This square bracket means molar concentration. So if you are doing a problem where you have to write the molar concentration, and if the grams are given, make sure you convert those grams to molar concentration. In this equation, these uppercase A and B are the reactants, and this lowercase a and b are actually the coefficients for those reactants. Similarly here, C and D are the product, and this lowercase c and d are the coefficients for that product. So rate of the forward reaction is directly proportional to the concentration of the reactants, and this is the molar concentration of the reactant, and we will write these coefficients as a power of these molar concentrations. We can say that the concentration is the only one factor that influences the rate of the reaction. So from this topic, you need to remember that higher the concentration, faster the rate of the reaction. Now, similar to any other mathematical expression, when we get rid of this proportional sign, we need a constant here. So constant for this reaction will be Kf. This K is specific for a particular reaction at a particular temperature. The rate constant K must be determined experimentally by observing how the rate of the reaction changes as the concentration of the reactants are changed. So few points that you need to remember for the rate constant are independent of concentration and changes with temperature. Okay, and third point is that this K is specific for a particular reaction. So that is what we have for the rate of the forward reaction, and we got the equation that the rate of the forward reaction equals constant for the forward reaction times the concentration of the reactants. Now let's write down the equation for the rate of the reverse reaction, right? Because this reaction proceed in both direction. So when we have some of the product here, then this product will starts to making the reactant back. So for the rate of the reverse reaction, I will write RR. Rate of the reverse reaction will also be proportional to the concentration of the product, which is actually the reactant for the reverse reaction. So these coefficients will become power, and these reactants, we are writing the molar concentration of the reactants here. To get rid of this proportional sign, we will use constant for reverse reaction. So here we have the equation for the rate of the reverse reaction. Now let's look at this, what we have in this graph. So this graph actually shows us the relationship between the concentration and the time. So this blue line is for the product and red line is for the reactant. So at time 0, our reaction only have reactants in it, right? So reactants concentration is somewhere at 1, little bit more than 1 molar, and product is 0 because the reaction didn't even started at time 0. As the reaction start, there will be only rate of the forward reaction, right? The only A and B are there, so there will be only rate of the forward reaction. But as this rate of the forward reaction is proceeding, the concentration of this reactant will starts to decrease, and that's what you are seeing here, that the concentration of the reactants will decrease. Okay, so the concentration of the reactant will decrease, and at the same time, there will be increase in the concentration of the product as the forward reaction is making more product. Okay, another point to remember about this K is that this K is a unitless constant. Here I have an example of a reversible reaction. So if you are running on a treadmill, you are in a constant motion. However, you are not moving forward or backward. And as fast as you can run forward, the treadmill is moving you backward. In other words, we can say that you are in the equilibrium with the treadmill. This example will help you understand the next topic, which is the chemical equilibrium. In this reaction, initially there is only hydrogen iodide. So there will be only forward reaction, and that reaction will be actually at the maximum because at time zero we have the maximum amount of the reactant present. So here we have the concentration of hydrogen iodide, which is the max, and here is the rate of the forward reaction, which is the maximum. Now, as the time pass, the reactants will start to consume. Now, at this time zero, as there is no product, so there will be no reverse reaction as well. So it is at time zero, the reverse reaction is zero, and the amount of the product is zero as well. Now, as the hydrogen iodide decomposes, there will be less of hydrogen iodide, so the forward reaction will start to slow down. So you can see here we have the rate of the reaction. So rate of the forward reaction will start to slow down. And when we have some of the product molecules, which is hydrogen and iodine in the reaction mixture, then this reverse reaction will speed up. And the rate of the forward reaction will keep decreasing, and the rate of the reverse reaction will keep increasing. And eventually, there will be a point where the rate of the forward reaction will become equal to the rate of the reverse reaction. At this point, the concentration of the product and the concentration of the reactant will be constant. And this point is called equilibrium. So equilibrium is a point where the rate of the forward reaction and the rate of the reverse reaction become equal, and the concentration of the product and the concentration of the reactant become constant. Okay, so these two words are not the same. Equal means they are like same, constant means they can be different, but they just don't change. This equilibrium is called dynamic equilibrium. The forward and reverse reaction occur at the same rate, so the change is happening, but the situation seems static. But in actual, the reaction is in continuous motion, and this equilibrium is called dynamic equilibrium. This equilibrium is called dynamic equilibrium as at this point, the amount or the concentration of the reactant and product does not appear to be changed, and it is because that the number of reactant molecules converting into the product and the product molecules converting into the reactant are same. So there is no change in the concentration of the reactant and product. Now, the definition of the dynamic equilibrium is that it is the state when the rate of the forward reaction become equal to the rate of the reverse reaction. You need to remember here that we are talking about the rate. So rate of the forward and reverse reaction become equal. But if we want to know about the concentration, then the concentrations of the reactant and product will become constant. There are many examples of chemical equilibrium around you. One example of the chemical equilibrium is hemoglobin. Hemoglobin is a macro or a very large molecule. The hemoglobin molecule has to be able to take up oxygen, as you can see in this equation, but it also has to be able to release the oxygen, and this is done through a chemical equilibrium, forward and reverse reaction, and this reaction takes place in different places in our body. So what actually happens is that at higher pressure or at higher oxygen concentrations, the hemoglobin binds to the oxygen, forming oxygenated hemoglobin, meaning in this equation the reaction will go towards the right. So if you recall the rate of the reaction depend on the concentration of the reactant. So if we have higher concentration of oxygen, then this rate of the forward reaction will be fast, and we will have more of the product in our reaction. When this oxyhemoglobin travels to a tissue that are deprived of oxygen, such as muscles where the partial pressure of oxygen or the concentration of oxygen is low, then in these areas, the oxygenated hemoglobin will actually release the oxygen and will convert back to the hemoglobin. In this example, we have a chemist performing a reaction. For this reaction, here is the balanced equation that we need 2 moles of sulfur dioxide, 1 mole of oxygen. We need some catalyst for this reaction, and it will make 2 moles of sulfur trioxide. So this is the equation, the plan. What this chemist did is he added these reactants, which is 2 moles of sulfur dioxide and 1 mole of oxygen. In the reaction mixture, he added the catalyst as well. He was expecting that all these reactants will convert into 2 moles of sulfur trioxide, but what happened is he only had 1.8 moles of sulfur trioxide, and at this point, the concentration of the product is constant and the reactant is constant as well. If you remember from the previous slide where we said that at equilibrium, the rate of the forward and reverse reaction will become equal and the concentrations will become constant. So at this point, this chemist actually waited quite a long time to see if there is any change in the concentration of the reactants, but there was no change, and that was the indication that the reaction is actually at the equilibrium. Here I have another example of dynamic equilibrium in chemical reactions. So for this reaction, we have the reaction between nitrogen and oxygen. So 1 mole of nitrogen, 1 mole of oxygen were supposed to give us 2 moles of nitrogen monoxide based on a balanced equation. But in actual, what happened is that we got only 0.040 moles of nitrogen monoxide. Chemists waited quite a long time, but there was no change in the concentration of the reactant and the product. It indicated that the reaction is actually at the equilibrium only after making this little amount of the product. Our next topic is to study direction of equilibrium. So there are some reactions that reach dynamic equilibrium very soon after the reaction began, and their equilibrium lies to the left or towards the reactant. The example that we saw in the previous slide where we started with 1 mole of nitrogen and 1 mole of oxygen, and after the reaction, we only got 0.040 moles of nitrogen monoxide and no change in this concentration, means that the reaction is at the equilibrium. So if you look at, we have mostly reactants in the reaction mixture and very little amount of the product. So this reaction actually reached to the equilibrium very soon after the reaction began, and we mostly have the reactants in the reaction mixture. So for this reaction, the direction of the equilibrium will be towards the left where we have our reactants. Okay. There are a few ways to indicate the direction of the equilibrium. One is by words. You can say the direction of the equilibrium is towards the reactant, or direction of the equilibrium is towards the left. Then we have some reactions that reach at the equilibrium when about half of the reactants are converted into the product. And for those reactions, the equilibrium is actually in the middle. So I don't have an image here, but let's try to understand with this example. So if, for instance, we are starting with 1 mole of nitrogen and 1 mole of oxygen, so total of 2 moles here, right? If we have 1 mole of nitrogen monoxide produced and then there is no change in the concentrations of reactant and product, and the rate of the forward and reverse reaction become equal, that reaction, the direction of that reaction will actually be in the middle where we have half of the reactant converted into the product. Now, the third type of the equilibrium is where the reactions reach equilibrium when most of the reactants have been converted to the product. And for those reactions, the equilibrium lies to the right or towards the product. This example as well, we saw in one of the previous slide. We started with 2 moles of sulfur dioxide and 1 mole of oxygen. and we were supposed to get 2 moles of sulfur trioxide, but we got 1.8 mole. You can see that we have most of the product produced and very small amount of the reactant left in the reaction mixture. So for this reaction, the direction of the equilibrium will be towards the right, or towards the product. Okay, so let's test what we have learned so far. You have to give answer in true or false. At equilibrium, concentration of reactant and product must be equal. If your answer is false, it is correct. They will be constant at the equilibrium, but they can be different. Second we have is at equilibrium, the rate of the reactions, which is the forward and reverse, must be equal. If your answer is true, then it is correct. So remember that at dynamic equilibrium, reaction seems to be forming no more product, but the reaction is still producing product, and at the same time, an equal amount of the product is being converted back to the reactant by the reverse reaction. So the rate of the forward and reverse reaction is equal, but the concentration of the product and reactant will be constant. Let's see what is equilibrium constant. Equilibrium constant shows the relationship between equilibrium concentrations of reactant and product. The equilibrium constant is specific for a particular reaction at a particular temperature, and the equilibrium constant, or K, must be determined experimentally. It is independent of the initial concentration of the reactants, but it does vary with temperature. So K equilibrium shows the relationship between the equilibrium concentrations of reactants and products. We will start with the definition of dynamic equilibrium, which is that an equilibrium state is achieved when rate of the forward reaction become equal to the rate of the reverse reaction under a set temperature. So we have learned in one of the previous slide how to write the equation for the rate of the forward reaction. So let's write down that equation again. So rate of the forward reaction is equal to constant for the forward reaction times molar concentrations of reactants. And remember, these coefficients that are balancing the equation will be the power for these molar concentrations. So here we have the rate of the forward reaction. Now the rate of the reverse reaction equals constant for the reverse reaction times the molar concentrations of the products. At equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. We can write it down like this. Okay. If these two rates are equal to each other, it means their right side of the equation is also equal to each other. We will solve this equation for Kf over Kr. Okay. Now, if you have to solve this equation for Kf over Kr, means you are bringing this Kr here in the denominator. This will remain here at the top. And you will bring the molar concentration of reactants under molar concentrations of product. This ratio of the rate constants that we have, Kf over Kr, this actually gives us a new constant, and that new constant is called equilibrium constant, or KEQ. Okay, so K equilibrium is the ratio of the molar concentration of the product over molar concentration of the reactants. This K equilibrium expression that we have derived here is specific for this reaction. So whenever we will be solving a problem related to K equilibrium, we have to write down this expression based on the balanced equation. So the things to remember about the equilibrium constant are same as we did for the constant for the forward and reverse reaction, that this is specific for a particular reaction, independent of the concentration, depends on temperature. Also unitless. Okay, let's do an example to determine equilibrium constant. So you will be using this equation and calculate the equilibrium constant. We did the practice how to write the equation for K equilibrium. It will be exactly this way. So you have a real equation. We did the practice with the generic equation. You don't have to do all these steps. You just have to remember that K equilibrium equals product over reactant. So start with a balanced equation, write the K equilibrium expression, and then find the equilibrium constant for this reaction. So you can do it at your own and then play the video to check the answer. Okay, so moles of ammonia, nitrogen, and hydrogen are given, and these moles are in 1 liter. For molarity, formula for molarity is moles per liter volume. So if you're dividing this mole by 1 liter, you will get the same molarity, right? So I will just write down that this is the molarity of ammonia. Here we have the molarity of nitrogen, and here we have molarity of hydrogen. Now let's write down the K equilibrium expression. So K equilibrium equals product over reactant. So product, we have NH3. We need molar concentration of NH3. This 2 will be the power here. Then we have reactants here. So product over reactant. We have 3 moles of hydrogen. So this will be the power here. Now we will simply plug in all the values that we have. So ammonia is 1.60, nitrogen is zero point 0.8, we have a square here. Hydrogen is 1.20 molar, and then you will be solving this equation to get the answer. So I have 1.85, 185, 185. And how many sig figs we need? We have 3 sig fig here, 3 sig figs here, and 3 sig figs here. So your answer is going to be up to here, and you will give 1.85 is the K equilibrium. You are not going to write down any unit with it. This will be the answer. So in this example, we will do the practice that if one of the equilibrium concentration is missed, but K equilibrium is given, then how to rearrange our equation and find the value of the missing equilibrium concentration. So in this example, the reaction is given. The K equilibrium for the reaction is given as well, and the equilibrium concentration of A2 and A2B means the product and one of the reactant is given, and you have to find what is the concentration of B2. So everything is given, looks like the right unit. I don't have to make any unit conversion here. Let's write down K equilibrium expression for this. So remember, your K equilibrium expression is product over reactant, like molar concentration of product over reactant. So here is the product. This 2 will be the power. Reactant is A2. We have a square here, and B. B is what you have to find. So like any other equation rearrangement, you will be making this X and move the variables wherever you need to move them. So B2 is what you need to find, means you want this B2 be at the numerator and by itself. So B2 will move up. You do not want this K equilibrium with B2. So this K equilibrium will come at the denominator. Okay, next we will simply plug in all the values given. So A2B is 0.596, A2 is 0.0224, and K equilibrium is 3.36 times 10 to the 18. Then do the calculation and you will get the answer. Next, the sig fig part, we have 3 sig figs here, 3 sig figs here. This leading zero is not significant, and then 3 sig figs here. So you will have up to this point, and when you do the rounding, you will get 2.11 times 10 to the negative 16 molar is the concentration of B2. These quantitative K equilibrium values can tell us the position of the equilibrium. Remember, we did this topic in one of the previous slides that the direction of the equilibrium or the position of the equilibrium can be towards the right if we have most of the product. It can be towards the left if we have most of the reactant, or it can be in the middle if we have reactants and products like half and half. But this K equilibrium can also help us determine the position of the equilibrium. So if this K equilibrium is large, which is close to or greater than 10 to the 3, 10 to the 3 is simply 1,000. So if it is close to or greater than 1,000, the equilibrium lies to the right. And there are mostly products in the reaction mixture. But if this K equilibrium is small, which is less than 10 to the negative 3 or 0.001, the equilibrium will lie more towards the left side and there will be mostly reactants in the reaction mixture. If the K equilibrium is close to 1, close to 1 means like plus minus 500. Okay, so if it is close to 1, the equilibrium lies near middle. This plus minus 500 looks like a broad range for saying close to 1, but that's how it is. Okay, so if it is close to 1, then the equilibrium is near the middle. If the K equilibrium is very, very small, very, very small means 10 to the negative 5, like we have 0.0001, then essentially there is no reaction. All of the reactants are just sitting there as is. If the K equilibrium is very large, which is 100,000, the reaction essentially goes to completion. Or we can say these might be the reactions, those are irreversible reactions. Now let's do some practice. So I have here some K equilibrium values given. How about you pause the video and find the direction of equilibrium for these K equilibriums at your own, and then play the video to check your answer. So for the first one, the K equilibrium is 1.0 times 10 to the 5, which is a very large number. So for this, we can say it is a complete reaction. Okay. When the K equilibrium is very, very small, which is 10 to the negative 4 here, You can either say when the K equilibrium is very, very small, which is 10 to the negative 4 here, you can say it is towards the reactant or to the left. And and you can even say that no reaction, because this is a very small number. It is even smaller than 10 to the negative 3. Next, we have K equilibrium 8.3. So for this, you can say it is in the middle. Next K equilibrium is 2 times 10 to the 3. So for this one, the equilibrium is mostly towards the right or towards the product. Next, we have 360, which is, we assume that plus minus 500 is close to 1. So for this as well, the direction of the equilibrium will be in the middle. Our next topic is disturbing a reaction that is already at the equilibrium. And this was actually studied by a scientist, Le Chatelier, and it is called as Le Chatelier's principle. The principle is that when any system at equilibrium is subjected to change in concentration, temperature, volume, or pressure, then the system readjusts itself to partially undo the effect of the applied change and a new equilibrium is established. So we will see in next few slides how a system readjusts itself to partially undo the effect of the change. So the first effect that we will see is the change in concentration at equilibrium. If there is increase in concentration of one of the component that is at the equilibrium system will shift away from the increase in concentration. Okay, so let's understand this with the example of a reaction A plus B giving a product C, and this is a reversible reaction. This reaction is at the equilibrium. Remember that the rate of the reaction depend on the concentration of the reactants. Higher the concentration, faster the rate. So if we are increasing the concentration of the reactants, the rate of the forward reaction will speed up. We'll be making more of the C or more of the product, and if the forward reaction is speeding up, the equilibrium will shift away from the increase in concentration, means it is going away from the reactant and moving towards the product. If you have more product, the position of the equilibrium is towards the product. Okay, so that is what is happening here. When we increase the concentration, equilibrium is shifting away from the increase going towards the product. Now, how does it fit to the Le Chatelier's principle that says that the systems readjust itself to partially undo the change? So if you see that the change is in the reactant side and that change is actually the increase, by shifting away from the increase, making more of the product, the system is actually undo or canceling the increase that we had in the reactant. Now, the second is decrease in the concentration of one of the component. Equilibrium system will shift towards the decrease in concentration. If we look at the same example, for this reaction, let's say we decreased the concentration of reactant. Okay, so when we decrease the concentration of the reactant, the equilibrium system will shift towards the decrease. So the decrease is towards the reactant, so the system will move towards the reactant. You have your reactants here, your product will start making more of the reactant, or the speed of this reaction will increase, will be making more of the reactant, and this fits to the Le Chatelier's principle that the system will readjust itself to partially undo the effect. So the effect is the decrease, and making more of the reactant is undoing the decrease that we had here. Let's do this example. Equilibrium reaction is given. Which way the equilibrium shift if the following stresses are placed on the system? Pause the video and find the answer. What would happen if hydrogen is decreased, if HCl is increased, if chloride is increased, or if HCl is decreased? You have to find which way this equilibrium will shift. Will it shift to the right? Will it shift to the left? So remember that increase in one of the component, increase in one of the components, system will shift away from increase, and decrease in one of the component, system will shift towards the decrease. Okay, so here are our key words that will help you identify which way system will move. Okay, so if hydrogen is decreased, so decrease is here in the reactant, system will shift towards the decrease, so the system will shift towards the reactants. Next, we have hydrochloric acid is increased. So we have increase in this area. So increase in one of the component, system will shift away from increase. So if increase is in the product, away from increase will again be the reactants. Okay. Next, we have chloride is increased. So we have increase in the reactant. So if we have increase in the reactant, system will go away from the increase, means it will go towards the product. The last we have hydrochloric acid is decrease. So if we have a decrease here in the product, the system will shift towards the decrease. So here we will have the answer towards the product. I hope you guys have the same answer. Okay, so the next effect that we will see at the equilibrium is the effect of temperature. And before we see how the temperature affect the equilibrium, we actually have to understand energy changes during a chemical reaction. And after that, we will see how temperature affects the chemical equilibrium. So most chemical reactions are accompanied by a change in energy. Energy is either given off or consumed during a chemical reaction. And there are two types of reactions based on energy change. One is called endothermic reaction, and the second is called exothermic reaction. We will see these two in detail in next slide. The reactions that consume energy are called endothermic reactions. The containers in which endothermic reaction is occurring will feel cold to touch. And for endothermic reactions, the energy sign that we use is positive. If there is energy given like 100 kilojoule and there is a positive sign with that, that is the indication that this reaction is actually consuming energy. Now, the reactions that give off energy and that given off energy is actually in the form of heat energy, those reactions are called exothermic reactions. The containers in which an exothermic reaction is occurring will feel hot to touch. And for exothermic reactions, the energy sign that we use is negative. So if you have an energy given negative 100 kilojoules, that negative will indicate that the energy is actually being given off in this reaction, and the reaction is exothermic reaction. Now the temperature change at equilibrium. So temperature change affects the exothermic and endothermic reactions in opposite ways. To determine the equilibrium shift caused by temperature change, we can assign heat energy either as a reactant or a product. So we will do that practice in next few slides. So endothermic reaction, as you saw that these are the reactions that absorb energy. We place the heat on the reactant side for endothermic reaction. Okay, So remember, endothermic reactions are reactions that absorb energy. Means if they don't get that energy, the reaction will not take place. If the reaction will not take place without that energy, means that is one of the reactant, right? That is why we put heat in the reactant side for the endothermic reaction. For the exothermic reaction, because the heat is given off, same to like the other products that are being formed in the reaction, right? So we will put the heat for exothermic reaction in the product side. So let's do this practice here. Given the following reaction and the value of delta E means energy is given, change in energy, assign the heat either reactant or product. Remember that we learned in the previous slide that this sign that is given with the energy will tell us whether it is being absorbed or released in the reaction. Now, if this positive sign means this energy is being absorbed in the reaction. And if it is being absorbed, means it is endothermic reaction and it is the reactant of the reaction. So if we have to assign this heat energy as a reactant or product, it will be here in the reactant side. I'll just say heat instead of writing numbers. Okay, so this will be the assignment of the heat for this reaction, that this is the endothermic reaction and heat is reactant. For this, given the following reaction and the value of delta E, assign the heat either as reactant or product. Now this time the sign for the energy is negative, means this energy is being released in a reaction. So if it is being released in a reaction, means this is the product of the reaction. Okay. Now let's see the effect of change in temperature for endothermic reaction at equilibrium. So an increase in temperature will increase the equilibrium to shift to the right, and decrease in temperature will cause the equilibrium to shift to the left. You can actually memorize this statement that we used in the concentration time as well, that increase in one of the component, this component can be concentration or it can be temperature. Okay, so you can just think of like increase in one of the component, equilibrium system will shift away from the increase, and decrease in one of the component, and those can be concentration and temperature, equilibrium system will shift towards the decrease. We already have learned where to assign the heat for endothermic and exothermic reaction. Now we just have to see if it is being increased or decreased. So here we have the example. So given the following reaction and the value of delta E, in which direction the equilibrium will shift if the temperature is decreased? Okay, so remember, the first thing you need to do is first you need to know whether this energy is reactant or product, right? So the sign for energy is positive, means this is being consumed and is the reactant. So I will write it down this in the reactant. Now, what will happen to the equilibrium shift? If the temperature is decreased, means we are decreasing the reactant. So if this side is being decreased, remember our rule, decrease in one of the component, the equilibrium will shift towards the decrease. So what will be your answer? Your answer will be equilibrium will shift towards the reactant. Okay. For this example, given the following reaction and the value of delta E, in which direction will the equilibrium shift if the temperature is increased? So how about you guys solve this problem at your own and then play the video to check the answer. So this negative sign indicates that this heat energy is being released in the reaction. So this will be the product of the reaction. Now, if the temperature is increased, means the product is being increased. And our rule is increase in one of the component will go away from increase. So it is going to go away from increase. So the direction of the equilibrium will be towards the left. Our next topic is equilibria for heterogeneous reactions. Chemical reactions that involve more than one phase are referred as heterogeneous reactions. And these reactions are easily identified because they involve reactants or products that are in solid or liquid phase. So here I have two examples. First reaction is we have silver chloride, state is given solid, and then the silver chloride is dissociated into its ions, giving silver ion aqueous and chloride ion aqueous. This is the one example. So look at this example and then look at the second example where we have sulfur dioxide gas, oxygen gas, and it is giving us sulfur trioxide gas. So in this reaction, all these three species that we have in this reaction, they are in the same phase, right? Gas, gas, gas. Whereas in this reaction, we have solid and aqueous, aqueous. So we have more than one phase is involved in this reaction. So if more than one phase is involved, then this reaction is heterogeneous reaction, and this is homogeneous reaction. So the equilibria that we learn in the next few slides will be for the heterogeneous reaction. It will be different from the equilibria that we learned in the previous slides. So the previous K equilibrium that we learned was for homogeneous reactions. So let's have a quick review of that. We learned about the homogeneous reaction. So if I have to write the K equilibrium expression, it is going to be product over reactant. So our product is sulfur trioxide, and then we have sulfur dioxide is the reactant, and we have oxygen as a reactant. So remember, this is the expression for the K equilibrium for a homogeneous reaction. You will see how this is different than the heterogeneous reaction in the next few slides. When we write the K equilibrium expression for a heterogeneous equilibrium reaction, we omit pure liquids and pure solids from the expression. If you remember the precipitation reaction topic, silver chloride is water insoluble, and this water insoluble salt is giving us some ions in the reaction mixture. If we compare this silver chloride with the example of sodium chloride, and we dissolve this sodium chloride in the water, this sodium chloride will actually give you 100% dissociation in the water. Means if you start with 1 mole of sodium chloride, it will give you 1 mole of sodium ion and 1 mole of chloride ion. So 100% dissociation of sodium chloride into its ions, and all of these are aqueous. This is a homogeneous reaction, right? But here we have water insoluble silver chloride. When we dissolve it in the water, it does dissociate, but a very less extent. And if I want to give some numbers, so for instance, I have 1 mole of this, I may get like a very, very small amount of silver and very, very small amount of chloride. So based on this dissociation, if you try to visualize your reaction mixture, in beginning you have 1 mole of AgCl, right? And after the reaction, this is your reaction mixture. After the reaction, you have 0.00001 of Ag plus. You have very small amount of chloride, and you have most of your silver chloride as is. So if I round this silver chloride to whole number, I will again actually get 1 mole of silver chloride, right? So my silver chloride is pretty much as is in the reaction mixture, no change in the concentration. So based on this, if I write my K equilibrium expression, which is product over reactant. So here are my products, right? So my product is silver ion, I have my chloride ion, And I actually have most of the silver chloride as is, right? So I will write down this, and then I have silver chloride in my reactant as well. And from here, the silver chloride will actually cancel out. So what do you have? You have only silver and chloride left, right? So this K equilibrium expression that you have for a salt which have a very less solubility in the water, we will be ignoring pure liquids and pure solids because their concentration is pretty much same before and after dissociation, so they will actually cancel out. So if you are writing the K equilibrium for heterogeneous reaction, you don't really have to do all this scratch work that I did. You will be simply writing it that this K equilibrium is the product of the solubilities of the product that we have. And you are not going to divide it by the reactant because we are ignoring the pure solids. And I explained the reason why we are doing that. Okay, so there is a big difference in writing the K equilibrium expression for a heterogeneous reaction. You will be ignoring pure solids and pure liquids, but for the homogeneous reaction, it will be product over reactant like this. So the example of a heterogeneous equilibrium is the equilibria of sparingly soluble salts. Sparingly soluble salts have low solubility, and the equilibrium is present between undissolved solid and ions in the solution. And when we are writing the K equilibrium expression, so remember that we will be ignoring pure solid, right? I'm not going to write down this. So if I have to write down K equilibrium expression for this reaction, it will be K equilibrium equals calcium times molar concentration of sulfate. And this K equilibrium for sparingly soluble salt is often called solubility product because it is the product of the solubilities of the ions. So we can just say KSP. You will see this terminology a lot. Okay, let's solve this problem. Sparingly soluble magnesium hydroxide. So when it says sparingly soluble means this is going to be our solid in the equation, right? So sparingly soluble magnesium hydroxide dissolves in water to yield a magnesium ion of 1.44 times 10 to the negative 4 molar. You have to write the balanced equilibrium equation for magnesium hydroxide dissolving in the water. We actually wrote many times the dissolving equations, but let's do it one more time. Okay, so when we write the equation for dissolving a substance in water, it does not mean reacting with water. So when we are writing this equation, we are not going to write down water in the equation. It will be only the substance itself. And this is a sparingly soluble, so it is solid. It will simply dissociate into its ion. Dissolving means dissociating into the ions. It will give you magnesium plus 2, that is the charge of magnesium. It will give you hydroxide ion, will actually give you two hydroxide ions, and the phase for ions is aqueous. Okay, so this is your balanced equation. Next, you have to write KSP expression for magnesium hydroxide. So if this reaction is at the equilibrium, the KSP when you are writing, remember the rule, you are going to omit or ignore pure solids and pure liquids. So your KSP is equal to magnesium, molar concentration of magnesium times molar concentration of hydroxide, and this 2 coefficient that we have will be the power of hydroxide. Next, you have to find what is the equilibrium concentration of hydroxide ion. So let's see what information is given. So the information given is we have the concentration of magnesium ion. Okay, so if the concentration of magnesium ion is given, what is the mole ratio between magnesium and hydroxide? It is 1 to 2, right? So you will be using the mole ratio from this equation to convert the moles of or the molar concentration of magnesium to the molar concentration of hydroxide. So this is 1.44 times 10 to the negative 4 molar magnesium plus 2. Use the mole ratio. 1 mole of Mg plus 2 is 2 moles of hydroxide. This will cancel and you will get molar concentration of hydroxide. The last step is calculate the value of Ksp for the reaction. So your Ksp is magnesium times hydroxide power 2. Okay, answer is 1.1943936 times 10 to the negative 11. We have 3 sig fig here, 3 sig figs here. So your answer will be 3 sig fig. This table have Ksp values for different compounds. Remember the Ksp or the equilibrium constant is specific for a particular reaction or a particular substance. So all these are specific to these compounds. Like for aluminum hydroxide, the Ksp is 1.8 times 10 to the negative 3. For barium hydroxide, it is 1.7 times 10 to the negative 6, and so on. You can see all these are very small values of Ksp. And if you remember the 5 numbers that we learned to determine the position of the equilibrium, which is if the K equilibrium is 1000 or more than 1000, then it is towards the right. And if it is less than 10 to the negative 3, then it is towards the left. Or if it is in the middle, then it should be like around 1. All these numbers are very, very negative or very, very small, which means all these salts are actually these sparingly soluble salts. When we are dissolving them in the water, they will give us a heterogeneous equilibrium where we are going to ignore the pure solid in the Ksp expression. So let's solve this problem. In this problem at 25 degrees Celsius, solubility of calcium phosphate in water is 2.6 times 10 to the negative 6 molar. What is the equilibrium concentration of cation and anion? So first of all, we have to write the balanced equation for this dissociation. We are dissolving calcium phosphate. This is a reversible reaction. It will give us 3 moles of calcium, 2 moles of phosphate. Okay. Solubility of calcium phosphate is given, which is 2.6 times 10 to the negative 6 molar. So you will be actually using your balanced dissociation equation in this case to find what is the concentration of cation and anion. If the solubility of calcium phosphate is 1s, I took 1 from here. The coefficient is 1. So if the solubility of calcium phosphate is 1s, the solubility of calcium ion is 3s, and the solubility of this anion is 2s. These 2, 3, and 1 are the coefficients of this salt and these ions. So if this is your S, to find the concentration of calcium, you will be just doing 3 times the solubility of calcium phosphate. And for phosphate, it will be 2 times the concentration of calcium phosphate. And you will just multiplying these and you will get your answer. Let's do this problem. In this problem, at 25 degrees Celsius, the solubility of iron 3 hydroxide in water is 4.49 times 10 to the negative 10 molar. What is the solubility in grams per liter? So this is simply the unit conversion. We know that M stands for moles per liter. So let's do the unit conversion for A. I will break M into moles per liter. We don't have to change liter because liter is needed in the answer. We will just change moles to gram. And when we are converting moles to gram, we need molar mass. So you have to find molar mass of iron 3 hydroxide. Formula for iron 3 hydroxide is FeOH3. Your iron is, okay, we are going to multiply this and then we will add. Okay, so 1 mole of iron 3 hydroxide is 106.88 grams. Okay, so that is the answer for A. For B, we have to find what is the molar equilibrium concentration of each ion. Since we have to find molar equilibrium concentration, we will be using this number, which is in the molar already. This is the molar concentration of iron 3 hydroxide. You have to find for each ion, means you have to write the dissociation equation of iron 3 hydroxide. So let's write down that. It is very important that you start with the right formula. Only then you will have the correct dissociation equation. So if this is your 1S, one solubility or one concentration, this as well is your 1S and this is your 3S. Okay, so these are the molar concentrations of cation and anion. Next, we have to find how many grams of ferric hydroxide could you dissolve in 20,000 gallon swimming pool, and a conversion factor is given. So this is basically a reaction stoichiometry with the help of unit conversion. So how about you guys do it at your own and then check your answer. Okay, let's do C. We are going to start with grams of ferric hydroxide. So ferric hydroxide, the name is changed here, but it is basically the iron 3 hydroxide. Okay, we should have 3 sig figs in our answer, 4.80 instead of 4.8. Okay, so how many grams of ferric hydroxide could you dissolve in a 20,000 gallon swimming pool? We have a conversion from gallon to liter. So let's convert these liters to gallon.